Neutrinos were first proposed by Wolfgang Pauli in 1930, however it took over 20 years for them to be detected experimentally. About 100 trillion neutrinos pass through our bodies every second, so why did it take so long to detect them? And why were they suggested in the first place? When the nucleus of a radioactive atom disintegrates, the laws of conservation state that the energy of the particle it emits must equal the energy it originally contained. However, in the 1930s, detectors were picking up much less energy than the nucleus was actually losing. At the time, there were several theories, but it was Pauli who conceived the idea that there must be an extra, undetected particle emitted by the nucleus. Enrico Fermi, while developing the theory of beta decay, named the mysterious particle the neutrino, which translates to little neutral one. If the neutron decays to a proton, electron, and neutrino, then energy, momentum, and spin are all conserved. So to answer our question, the neutrino was proposed to balance an equation that wasn't quite adding up. At a South Carolina nuclear weapons laboratory in the 1950s, 2 large water tanks were stationed outside a nuclear reactor that, according to calculations, should have been making 10 trillion neutrinos a second. The detector did manage to spot some neutrinos. The scientists had finally established that the elusive particle was real. Now the puzzle was the amount detected. They found about 3 an hour, a far cry from the calculated trillions a second. Over time, the search was scaled up and refined. Notable experiments include the detector installed 4,850 feet underground in the home state gold mine, which ran for over 30 years, and Super Kamiokande in Japan. Super K was set up in 1996 and consists of 50,000 tonnes of water in a dome tank covered with 13,000 light sensors. The sensors detect the flash of blue Cherenkov radiation made when a neutrino collides with an atom in the water to create an electron. Despite the scale and sophistication, physicists still didn't achieve the numbers expected. The mystery continued until 2001, when the Sudbury Neutrino Observatory found that neutrinos spontaneously oscillate between 3 flavours. Previous experiments had detected few neutrinos because the instruments were tuned to just one flavour, and were missing the others. Furthermore, because only particles with mass oscillate, they established that neutrinos couldn't be massless as previously thought. There is still so much to learn about neutrinos, and many current experiments hope to unravel their secrets. The Cotrin spectrometer hopes to determine their mass by measuring atoms before and after they decay. IceCube, which is based in Antarctica, has over 5,000 blue light sensors pointing towards the ground to detect neutrinos from the sun and outer space that are coming through the planet from the north. The Earth blocks cosmic rays, but most neutrinos travel through the 8,000-mile wide planet as if it weren't there. We hope that neutrinos from outer space might carry information about supernovas or colliding galaxies. Who knows what more we might learn?